Alright, this video we are focusing on titrations, which are also one of your core practicals. I'll probably do some of the exam questions in this video as well, so apologies in advance if it's a little bit longer. I'll try not to ramble too much. So I've drawn out what a titration would look like. You've got this long thin piece of glassware called a burette, and then underneath you would place your conical flask with some form of indicator. And if we look at why we're actually doing a titration, alright, the whole point of it is to find out the exact volume of one solution. So I've said HCl, that's in my burette, that reacts with a known volume of another solution. So I've said 25 centimeters cubed of NaOH. That's the point. At the end of a titration, I will know exactly what volume of HCl I need to react with 25 centimeters cubed of NaOH. And you might ask why. Why is that information even useful? It's actually got a number of applications. If we didn't know the concentration of one of these solutions, we could use a titration to work out what that concentration is. When you find concentration, you can then convert that into mass. So one of the practicals I just did with my A-level students, we worked out the mass of iron in an iron tablet. You can use it to determine percentage purity. So again, if you had an iron tablet, you can work out how much of the iron tablet is actually iron. If you had, the other one we do is we have like a brass nail, and we work out how much of the nail is actually brass. So you can use titrations to do this. And then the final, most kind of simple basic application is you can just make a pure salt. And this is the first one that I'm going to focus on. How do we use a titration to make a pure salt? Okay, so I give you an example of an equation. If I want to make a salt, I'm going to react an acid and a base. So I've got acid and a base reacting, and the salt I'm making is sodium chloride. Now, in order for this to be pure at the end, the HCl and the NaOH need to react with each other in exactly the right quantities. And to figure out when the reaction is done, I'm going to be using an indicator. The color change will tell me when the reaction is complete. Once I've just got salt and water, because these guys have reacted in exactly the right quantity, so they're no longer present, I'll be able to just evaporate the water and be left with a pure salt. Okay, so if I had my NaOH, so my base in a conical flask with an indicator, and I tried to just pour the HCl in from a beaker, even if I did this slowly, pour in a little bit of HCl, give it a good swirl, pour in a little bit more, give it a good swirl, I don't have enough control when I'm pouring from a beaker to be able to stop at exactly the point when that indicator changes color. I am definitely going to add too much HCl. And once you add excess HCl, you've got no way of removing it again. Okay, so what you'll end up with if you add excess HCl is the NaOH will have fully reacted, it won't be there anymore, and you will have sodium chloride and you will have water, but that extra HCl you added, that will remain in the flask and you won't have a pure salt. The advantage of the burette, which is what we use in the titration, advantage number one is it's got a tap, okay, and that tap will allow you add your solution dropwise when you get close to the end point and prevent you from adding too much HCl. So it gives you control, okay. The other thing is after you do this particular reaction, all right, in my conical flask, even if I did have excellent control and I managed to add exactly the right quantity of HCl to properly neutralize the NaOH, I'm going to have salt, water, and I'm still going to have that indicator in there. You will still have indicator left in the flask, and that means that you're going to have to repeat the experiment again without the indicator. Now, if you're using a beaker, just say you'll say, I added roughly 30 centimeters cubed of HCl in order to get that color change. Okay, when you take the indicator away and do the practical again without the indicator, this is what you're basing it on. You're basing it on the fact that you think you added 30 centimeters cubed when you did have the indicator change color. But the resolution on a beaker, it's not high enough, okay? That's not an accurate value. If you look at a burette, it's got lots of what we call graduations going the whole way down the side. So we say it has got a high resolution because with the burette you can record volumes to 2 decimal places. So I can say I've added 24.25 centimeters cubed, and I know that to 2 decimal places. So when I remove the indicator and I go again, I know I'm adding the right volume of HCl to bring about that change. All right, so in your questions, I ask you to do question 1 and 2. I'm going to kind of help you with question 2, just so you don't waffle too much. All right. So question 1, I just said titrations are carried out to determine the exact volume of one solution that reacts with a known volume of another. Give 2 reasons why this information is useful. All right. The one I was just talking about is that you can make a pure salt. The other application is you can work out an unknown concentration, and we're going to look at that one in a second. Determine unknown concentration, or you could say determine percentage purity. All right, but the next bit here, this is a potential 6 marker. A student plans to make a salt by reacting a solution of acid with a solution of base. Write out the steps they need to take. Okay, first thing we're going to talk about is how we're going to get exactly 25 centimeters cubed of one of our solutions into the conical flask. This has to be done super accurately. A beaker is not going to cut it, neither will a measuring cylinder. You need to use a piece of glassware called a pipette. Not one of those little dropping pipettes. It's a pipette that looks something like this, and you use what's called a pipette filler, which sometimes looks a bit like this. You use this kind of pipette filler, a suction device, and pipettes measure one volume and one volume only, and the volume they measure is typically 25 centimeters cubed. So it's just, again, it's got a high resolution. It will allow you to very accurately measure the volume of the solution that's going into the conical flask. So mention that you're going to use a pipette, and then you're also going to add some indicators. So if I'm writing this out step by step, I'll say using a pipette I will add 25 centimeters cubed of the NaOH to a conical flask. Instead of just saying indicator, I'm going to name one. I'm going to say phenolphthalein. It doesn't matter whether the HCl or the NaOH goes into the conical flask. You don't have to say 25 centimeters cubed, although that is the standard volume used, but you should specify that it's a known volume, and you should specify that you're using a pipette. So once you've got your NaOH in your conical flask, you're going to be adding the acid from the burette. So because I put NaOH in the flask, the acid has to go in the burette. So I'm just going to say add it from the burette until the colour changes. Because I've said phenolphthalein, I know that the colour change is going to be from pink to colourless. So phenolphthalein is pink in the alkali, it will go colourless in an acid, and then towards the end I'm going to add a dropwise. Okay, so on the mark scheme it wants some fine detail, specifying the indicator, saying add dropwise, that's you giving fine detail. Once you've got that colour change, you want to note the exact volume of HCl added, and you're going to note that volume to 2 decimal places. That's not enough, however. You need to repeat it multiple times because you need to get concordant results. So they're results that are within 0.1. At GCSE, I think they allow you to say 0.5, but at A level we say 0.1. Once you've got your 3 concordant results, you're then going to calculate the mean titer. That's what it's called. The volume added from the burette is called the titer, and you're going to get a mean titer. So at this point, you know exactly how much acid is required to neutralize that NaOH. You don't need the indicator anymore. You know when the color change is going to take place. So then you're going to repeat it again without the indicator. And this means that in the conical flask at the end, you'll have no indicator in there. All you'll have is pure salt and water. Your final step then to obtain that pure salt is to evaporate the water using crystallization. Okay, you do need to write this. All right, they've asked it before as a 6 marker, and you're going to see it when we look at fertilizers, actually, because we're going to use titrations again when we look at fertilizers, and that's when they asked it. Okay, so just make sure you can describe this process in relevant detail. Alright, the other application we said was working out an unknown concentration. So I'm going to say that I don't know the concentration of HCl, and then the NaOH. If you've got one unknown, you need to know the other. So I'm going to say that the concentration of NaOH is 0.1 moles per decimeters cubed. So there's one that you know, there's one that you don't know. And the one that you know, this one is called your standard solution. So a standard solution is just a solution whose concentration is accurately known. And how do you know that it's accurate? How do you know for sure that sodium hydroxide has a concentration of 0.1 moles per decimeters cubed? Well, the answer is you have to make it yourself. All right, you make that solution yourself, and you make it so accurately that you know it's going to be 0.1 moles per decimeters cubed. So how do you make up an accurate standard solution? All right, so I've just made up numbers here. Actually, I didn't do the calculation, so these numbers can be very wrong, right? But I'm making up a standard solution. I'm making up of sodium hydroxide, all right? So what I would do, sodium hydroxide initially is a solid, right? It's ionic, it's going to be solid. And I'm going to weigh out the mass of sodium hydroxide that I need for the concentration I'm trying to make. And I weigh that out using my little mass balance. And let's say I weigh out 2 grams of sodium hydroxide. Then I need to dissolve that sodium hydroxide in some water. So I'm going to add in like 50 centimeters cubed. It doesn't really matter how much water. You just add enough so that the solution, so that your salt is fully dissolved. You've got it there still in this beaker. Then in order for it to be super accurate, you're going to use what's called a volumetric flask. So you're going to take your dissolved salt and you're going to pour it into this volumetric flask. Now the issue is you're probably still going to have traces of the solution left in the beaker. So then you take some water, you squirt it into the beaker, you give the beaker a good rinse, you add the rinsings into the flask. You do that multiple times to make sure that every single speck of NaOH has been transferred to the volumetric flask. And once you're sure that you've got it all into the volumetric flask, then drop-wise, all right, there's going to be a little line here on your volumetric flask, and drop-wise you're going to add water all the way up to that line so that you've got a solution of 250 centimeters cubed, all right? So just like a pipette will only measure one volume, so will a volumetric flask. There's no lines on it other than this one line on the top, and it measures 250 centimeters cubed and nothing else. So you're going to keep adding water all the way up to the line, and once you have it up to the line, you put a little stopper on it, you invert it a few times to make sure it's mixed, and there you have your accurate solution. All right, so this process of adding all the rinsings ensures that you get the right mass in, and then the fact that, again, the volumetric flask is what we call a high resolution. It's a really accurate piece of glassware for measuring out exactly 250 centimeters cubed. Right, press pause and just do questions 3 and 4 on your little sheet. All right, there's question 3. What's the standard solution? A solution of known concentration. What do I use to make it up? I use a volumetric flask. All right, next up we're going to go to page 19 and we're going to do one of the exam questions. So we said we can use this to work out an unknown concentration, so there is a calculation involved. So here they've given you a reaction that was carried out during a titration. You've got your acid reacting with your base, forming a salt in water. And they tell you that when you were doing this, you needed 12.15 centimeters cubed of the acid. They tell you the concentration of that acid. They also give you the volume of the base, and they're asking you for the concentration. All right, so this is typical. You will always be given 2 volumes and 1 concentration. You will always be asked to work out the second concentration. I'm going to do this in a little table, all right? It's always going to be the reactants, the acid and the base, and down the side I'm going to have volume, concentration, moles and ratio. So it's a different formula triangle. It's got moles on the top, concentration and volume at the bottom. So the volume of H2SO4, just make sure you put the numbers in the right place. So 12.15 of dilute sulfuric acid, that's the volume of the acid. It's in centimeters cubed. I need to put it into decimeters cubed by dividing by 1000, all right? So that's the volume in decimeters cubed. It tells me the concentration of the acid as well is 0.140. I can also fill in the volume of the base, 25 centimeters cubed. Again, I put that into decimeters cubed, but the concentration I don't know. The ratio I get from my balanced equation. There's nothing in front of H2SO4. There's a 2 in front of KOH, so I've got a 1:2 ratio. Using my triangle to work out moles, it's going to be concentration times volume. When I times those two, I get 1.701 by 10 to the minus 3. I've got a 1:2 ratio, so I need to multiply that by 2. I get 3.4? I can't read it. Surely it is. 3.402 by 10 to the minus 3. And once I've got moles, I divide it by volume and I work out concentration, which is 0.13608. I'm just going to round that. It doesn't say a number of significant figures. On the mark scheme, they give the answer as 0.136, but it doesn't specify, so you're not going to be penalised for that. And you're going to get 4 marks for being able to do that. I want you to have a go at the next one. So if you turn the page, question 5, really similar. All right, really similar. A little bit more kind of fluff, but have a read through that and do question 5 for yourself, please. Yes, this one's done the same way. Okay, volume of the acid is 25. I put that into decimeters cubed. You're not given the concentration of the acid, you're given the volume of the base, you're given the concentration of the base. I multiply these two to get moles, then I divide by 2 because that's my ratio, and once I've got moles, it's moles divided by volume. My final answer is 0.097. Again, it doesn't specify the number of decimal places. 0.097 is what's given on the mark scheme. Okay, if we just look at some other exam questions now, it's really important that you can actually read a burette. So here you can see it starts there at 1 and you're reading down, okay, so you're not saying that this is 2.55, you're reading down and you're saying if that would be 1.1, 1.2, 1.3, 1.4, it's not quite at 1.5, so you're reading it as 1.45. So this is called the meniscus, this curve, and we say that we read from the bottom of the meniscus, so you're reading from that point right there and it's 1.45, and you have got to record to 2 decimal places. Similarly here, you're reading down, so it's going to be 27 point something, that's 27.567, and again the bottom of the meniscus is between 7 and 8, which makes it 27.75, always recording to 2 decimal places. If I'm starting at 1.45 and ending at 27.45, you just need to get the difference between these two in order to get the volume added, alright, so that's what's called the titer. So the actual volume, the difference between these two, is called the titer, and when you subtract these, you're going to get 26.3. Now if you wrote 26.3, you wouldn't get the mark. That's not a suitable number of decimal places. It's always 2 decimal places, so your titers should always end in a 5 or a 0. If you don't give it to 2, you're going to lose one of the marks. Another question down here, okay, they've given you the titers. Again, you'll see that they all end in a 0, all to 2 decimal places. They want to know which ones should be used to calculate the mean. You never include the rough, okay, ever, so just discard that straight away. Then you're looking at these 3. You want concordant results, okay, they need to be within 0.1 of each other. 24.9, 25, they're within 0.1. So you'll add these two together, divide by 2 to calculate the mean, and you're going to get 24.95, again to 2 decimal places. The other thing they love to ask is to make improvements. There's quite a few questions that you're going to do where they ask how you'll make it more accurate. This one was slightly trickier, I think, because rather than letting you kind of just give your rehearsed answers, they gave you a picture and they wanted to know specifically what this student had done wrong. So it says he took the burette from the cupboard, closed the tap and filled the burette with the correct solution, added it drop by drop until the indicator changed. Now there's 2 things wrong from the picture that you need to be able to spot. Number 1, okay, that's the last graduation mark and he's filled it too high. Okay, so first thing they've done wrong is they have overfilled the burette. Second thing they've done wrong, okay, is they haven't filled below the tap. When you're filling the burette, the tap is initially supposed to be open, so this part fills and then you close the tap again. It's calibrated so that this part has to be filled, so you have to fill below the tap. And you needed to spot those 2 mistakes. Another common mistake people make is they leave the funnel in the burette. You use a funnel when you're filling it, but you have to take the funnel out. So if they had a funnel drawn in there, that would be another mistake. If you leave the funnel in, drops can fall from the funnel and that will interfere with your titer. The other mistake the student made, it says they took it from the cupboard and they filled with the correct solution straight away. You always need to, usually you'll wash it first, you'll wash it or rinse it with water, and then to remove that water you then rinse with the solution it's about to contain. So if your burette was going to contain HCl, you'd give it a little rinse through with water, then you'd rinse out the water with HCl. So you'd let the HCl flow the whole way through and then you would fill it up properly. Alright, there's a few other things accepted. You'll see that on the mark scheme. Alright, most of the other exam questions are just about the colour of the indicator and about things that you can do to make it more accurate. But recently, the last 2 years in particular, they've started asking questions like these, okay, about errors that students make and how it affects the titer. So I've given you a scenario here. You've got your acid in the burette, you've got your sodium hydroxide in the conical flask, and your sodium hydroxide is your standard solution, which means you added it using a pipette, okay? This isn't standard. You do need to make sure that the standard solution is in the conical flask. Sometimes they can put the standard solution in the burette, so make sure you read the context that you are given. And then we're going to look at these errors, and we're going to explain whether they'll give a bigger titer. Okay, bigger titer means you need to add a greater volume from the burette than everyone else. So just say you guys are all doing it together and everyone had 25 centimeters cubed from the burette and you have to add 27 because you've made some sort of mistake. Smaller titer means you're adding less from the burette than everyone else to get that color change, and no effect, you're adding the same amount from the burette as everyone else. So we're going to go through some of these scenarios, all right? If too much water is added to the volumetric flask, what effect will that have on the titer? Okay, I'm using my volumetric flask to make up my sodium hydroxide solution, and that goes into the conical flask. Okay, if I put too much water in my volumetric flask, then my solution is too dilute. If it's too dilute, then I end up with less sodium hydroxide in my conical flask than I'm intending. If I've got less sodium hydroxide in my conical flask, then I'm going to need less HCl to neutralize it. Therefore, my titer is going to be smaller. Okay, so too much water is added to the volumetric flask. I'm going to have a smaller titer than everyone else. Okay, the next one, the pipette. Okay, so I've been rambling away for ages, not realizing that my video was paused. I can't remember the last thing that I actually recorded. I'm just going to start from here. Apologies if I have already said this, all right? So the other question that they seem to like to ask is mistakes a student makes and how it affects the titer. So the titer just refers to the volume being added from the burette. If you're getting a bigger titer than everyone else, that means you're adding more from the burette than everyone else is. Smaller titer, you're adding less to get the color change than everyone else is, and if it has no effect, you're adding the same amount as everyone else to get that color change. With these questions, you can't learn them off because they can change what's in the burette and what's in the conical flasks. You need to read your situation. I've given you the acids in the burette and your standard solution is in the conical flask. That doesn't have to be the case, so just make sure you read it. First situation here is I'm saying too much water is added to the volumetric flask. What effect will that have on your titer? All right, so if we have a look at what's going on, if I'm making up my standard solution, I'm making it in my volumetric flask. If I add too much water, then my standard solution is more dilute than it's supposed to be. If it's more dilute than it's supposed to be, even if I use my pipette properly, I'm adding less moles of sodium hydroxide into my conical flask than I am supposed to. If I've got less NaOH in my flask, then I'm going to need less acid to neutralize it, and my titer is going to be smaller than everyone else's. Okay, so the first example there, it's going to be smaller. You're adding less NaOH, so you need less HCl to neutralize it. Next situation, the pipette contains some water. So even if I've done a top job making up my making up my standard solution, if I have water in my pipette, then I'm not going to transfer a full 25 centimeters cubed to my conical flask. Some of that will be water, and that means I'm transferring less sodium hydroxide than I'm supposed to. If I'm transferring less, then I'm going to need less to neutralize it. So again, my titer is going to be smaller. Now the next one is a little bit trickier. The conical flask contains some water. So that means that there was a little bit of water in here when I added my solution. This actually doesn't have any effect, okay, and I'll explain why. If you use your volumetric flask correctly and you use your pipette correctly, then you do transfer the correct number of moles of sodium hydroxide to that flask. The sodium hydroxide will not react with water. Water can't neutralize sodium hydroxide. So the number of moles of sodium hydroxide will be unchanged. If the number of moles of sodium hydroxide is unchanged, then your titer is going to be unchanged. Okay? All it's going to mean is if you've got some water in there, you're going to have to swirl your flask a bit more in order to get the HCl and the NaOH to react. You've got the correct number of moles in there though, therefore no effect on your titer. The other way they can sometimes ask this is they'll say that some of the acid gets stuck around the side of the conical flask when you're adding from the burette, and you can use a little kind of wash bottle to rinse down the sides as you're doing the titration, and they'll ask if that has an effect, and the answer is still no. As long as you've used your volumetric and pipette correctly and you've got the right amount of NaOH in there, adding water, diluting it after the fact doesn't make a difference. You can dilute it afterwards, you just can't have it more dilute before you add it into the conical flask. The next three I'm just going to let you have a go by yourself. Try and do D, E and F. See if you can work out the effects on the titer. Alright, the last three should be bigger, no effect, and bigger. Hopefully D is okay, alright? If you've got some water in your burette, then you don't have as much HCl as you think you do. If your HCl is more dilute, then you're going to need more of it to neutralise your NaOH. So D is going to be a bigger titer. If they're all taken from the top, it's not going to have any effect. I've drawn that out here. Just say this is your initial and this is your final. You're always working out the difference. So if you measure the distance between the bottom and between the top of the meniscus and the top of the meniscus, the difference is the same. We read from the bottom because it's easier and you're more likely to be accurate if you read from the bottom. But because you're dealing in difference, if you make the same mistake twice, it effectively cancels out and it's not going to have any effect. The burette contains an air bubble. That's a bit harder. If the burette contains an air bubble, just say you've recorded that you've added just say you think you've added 27 centimeters cubed. You haven't, okay? Because of your air bubble, you might have only added 26.5 centimeters cubed, okay? But the value that you've written down on your piece of paper is 27, and it's bigger than everyone else's because of that air bubble. So it's not that you've actually added more, but it's that your recorded titer is now going to be higher. You haven't added as much as you think you have, because some of what you've added has just been air, but your recorded value will be higher. And of course that value is supposed to be to 2 decimal places, not just as a whole number. I think that's essentially it. So, right, you obviously have to finish off your exam questions. Apologies if this is longer video than normal, but realistically we did not do well in the titration questions on the mock, so it is something that we are going to have to work at.